Good afternoon, everyone. So I'm Natalie Pham, and I'm excited to be here today to present my work on estimating frequencies for multi-sinusoidal signals, and this could have further applications to imaging, radar, and signal processing. So we introduced a novel approach using Fourier neural operators to estimate frequencies for multi-sinusoidal signal with high frequency, especially for noisy samples. And our shallow FNO frequency module predicts frequencies and amplitude from noisy signal by minimizing the chamfer distance. And unlike the conventional convolutional neural network approach, this significantly reduces the training data required and shorten training times. So results significantly indicate that shallow FNO frequency module able to predict frequencies far and under high noise level and demonstrating robustness and generalizations. The study highlights its potentials in efficiently solving challenging signals processing problems. And for future work, we are planning to incorporate our frequency estimation modules into a variational autoencoder models to reconstruct clean signals. Thank you.
Finding new molecules and predicting reaction pathways is a fundamental yet challenging problem in chemistry. Predicting reaction pathways is important because it helps discover new molecules, and it also helps find transition states, which tell us how fast chemical reactions happen. Hello, my name is Miko Stuhleiter, and I'm a fourth-year PhD student, and I've been researching reaction networks. Reaction networks are discrete network representations of chemical space, where chemical space is all molecules for a given set of atoms. Within reaction networks, nodes are a collection of molecules and edges are transformations between them. My work here today will be showing how we can embed reaction networks into Euclidean space to find reaction pathways more efficiently. If you want to learn more about my work and how to kind of embed these reaction networks into Euclidean space, you can see me at poster number 2. Thank you.
Hi, everyone. My name is Ashley Valentina Schwartz. I'm a computational science PhD candidate. So birth defects are the leading cause of infant mortality, yet 65 to 75% of them have unknown causes. Oopsie, I don't know what happened to my thing. Yeah, environmental factors are known to play a role, but it's increasingly difficult to explain these outcomes because of their multifactorial nature. So to address this, I worked with the California Department of Public Health to compile a data set of over 550,000 births throughout the state of California, integrating health information, demographic information, and environmental information. And to explain these relationships, I developed a multi-layer network model to inform a machine learning model for birth defect prediction. The model achieves an accuracy of approximately 90%, but most importantly, when removing environmental factors, the performance drops by nearly 50%, emphasizing the critical role of the environment. Further analysis using interpretable machine learning reveals that impaired water bodies, such as the Tijuana River, is an important plays the most role in birth defect outcomes. So ultimately, this research shows that environmental implications play a key role in birth defect prediction and provides a framework for better risk assessment and prevention strategies. If you'd like to learn more, please talk to me. Research poster number 3.
Good afternoon. As we enter a new era of space exploration, there is a demand for technological advancements. For technological advancements supporting the complex and dynamic environments in space, including onboard or autonomous navigation. One such method is called optical navigation, or OpNav, which uses images of the moon and image processing to estimate a spacecraft's position relative to the moon. However, this process is computationally expensive, limiting a thorough analysis. My name is Emma, and my research proposes a model to efficiently approximate these measurement errors along Earth-Moon or cislunar space using interpolation of the pre-computed data. These approximations are incorporated into a common filter with a bias estimator and Monte Carlo simulations for an overall comprehensive assessment of autonomous OpNav at a reduced computational cost. And if you would like to learn more, you can visit me at poster 4. Thank you.
Hey everyone, I'm Rebel and I am working on machine perception. And specifically, how do I get a state-of-the-art visual SLAM algorithm that normally would run on a desktop computer, working on something as compute efficient as, well, maybe inefficient, as a ARM core running on a tiny drone. Our research looks at how we can approximate frame data to achieve higher accuracy in the worst case situations where a machine, such as a small drone, thinks it is versus where it actually is in real life. The idea here is if we can prevent this error from growing or keeping it to some threshold, we can prevent the drone from crashing into the wall in the worst case, or allow for larger openings so that the drone can fly through. And if you want more information, visit me at poster number 5. Thank you.
Hi, everybody. My name is Edward Finkelstein. I'm just trying to get a particle to the top of the hill. How do we do that? Well, just use Newton's second law, right? Mass times acceleration equals the force, which is the negative derivative of the potential energy. Okay? And we model the potential energy as a trap and a hill. And we want to use a neural network to move the hill to the left and to the right to get the particle from the bottom to the top as efficiently and as smoothly as possible. Well, I don't care. Well, we can apply this problem to controlling solitons, which are stable wave-like structures that maintain their shape and form long after propagating through various materials. So they're very robust and great for communication, and they also appear in various physical systems, like Bose-Einstein condensates, fusion reactors, optical fibers, right? And if we can control these, then we can exploit their robust capabilities while being able to confine them, for example, in the fusion reactor and harness great energy producing capabilities. That is my project. Thank you for listening to my 1-minute first presentation.
Oh, hi everyone, my name is Yu. I'm going to introduce a still ongoing project since I was a master's student. It's basically about making a soft probe, and I'm in charge of calculating the 3D cardiac strain. So 3D cardiac strain is always a very important topic, and it reflects the malfunctions of the heart, or like people use it to evaluate whether it's healthy or not for a certain patient. And here we're trying to create the 3D cardiac imaging. And it's basically both of two parts. One is called the principal component analysis, and one is like we borrow the model from the ALS project, which is an existing model, and we'll incorporate our vectors into that 3D model. And the most interesting part of this project is the PCA, because when we're using block matching method to evaluate the strain vector, there tend to be some outliers right there. Like you see the blue vector, this always happens. And the PCMS, because principal components represents the direction with the largest variance of the data. So by applying PCA, we can get rid of those outliers and make our data more precise, I would say, and then even make the data more smooth. So if you want to learn more about this, you can go to the poster 7. Thank you so much.
Hello, my name is Zoe Holzer, and my research is on investigating the impact of the COVID-19 pandemic on the transmission and evolution of viral pathogen agents. So the idea is that during the COVID-19 pandemic, there was a lot of social distancing measures and stuff like that. So people had reduced contact, and basically viruses other than COVID should have been affected. So I use genetic sequence data to infer effective reproduction number, which is used to evaluate the effectiveness of interventions on viruses, and also effective population size, which is used to basically look at the impact of these interventions on the evolution of the viruses. So if you would like to see my results on influenza, RSV, dengue, and COVID, please come to my poster at number 8. Thank you.
Hello, everyone. My name is Tyler Collins, and I'm a first-year PhD in the Computational Science program here at SDSU. I work with Dr. Sara Adibi in the Computational Mechanics lab, and currently we are exploring polyurea's high-velocity impact behavior through molecular dynamics. So polyurea is already, or is a polymer already used in construction, aerospace, and defense. But we're especially interested in its use or its role as a reinforcing layer in protective equipment and blast-resistant applications. So what makes it so special is its molecular structure. Hard and soft domains give it strength and flexibility, but when something fast like a projectile hits it, it stiffens and absorbs energy. So to explore this, we ran an all-atom simulations in LAMPS, emulating a projectile impacting 1,000 meters per second. We observed how energy dissipates through heat and hydrogen bond breaking, as well as different failure modes. If you'd like to learn more, you can see me at poster 9. Thank you.
Hello everyone. So I'm Mingxiu Liu. So today my topic is my work, the Flex drug. We build a domain-informed framework for precise and stable compositional drug editing. So we all know drug editing is very important. So the traditional way is like time consuming and very complicated. But right now we want to merge the large language model into that kind of flow to help build a new efficient drug editing procedure. So the core for all these procedures, of course, is the conversational. That is, for example, we can, as a user, like you can you can ask a question. For example, you can make this molecule more soluble in water, and then it will transfer to the PDDS, which is the pumped design model that we designed. And this model would incorporate with the external, the molecular knowledge and help us to design very helpful pumped. Then it will go into our local deployed and knowledge fine-tuned large language model, and to get the final drug editing answer. And there's two main points, to ensure the result we generated is always correct, the value. We have two key innovations. The first is we feed a lot of knowledge into our large language model that is over 1.4 million small molecules knowledge and over 500K protein drug knowledges. And we have another model that can define if the output is valid or not. And that is the retrieval database and the domain feedback. If it is not correct, we're gonna retrieve a new similar drug, and we can just feed that back into the large language model again to get a better answer. The iterative process continues until the end. Thank you.
Effective management for preventing and controlling of infectious diseases relies on accurate estimates of reproduction numbers, the most critical epidemic thresholds that represent the average number of secondary infections. And existing methods to compute these indices fail to accurately represent the nuances of indirect transmission via vectors, potentially limiting their accuracy in complex epidemiological settings. Hi everyone, my name is Audrey, and our project develops a novel framework for data-driven modeling to accurately estimate reproduction numbers of airborne and vector-borne diseases. And we then apply this methodology for H1N1 data affecting Washington State University students in 2009, as well as on current dengue fever pandemic data of Bangladesh. And this novel approach allows us to better capture the dynamic interaction between vectors and humans, ultimately leading us to more effective public health policy implementation. So if you'd like to learn more, please come to poster number 11. Thank you.
Hi, everyone. My name is Anand Srinivasan. I'm one of Dr. Castillo's students. In this research, we aim to investigate the use of high-order mimetic methods for solving turbulent flows with Navier-Stokes equations. The mimetic methods are based on discretizing and mirroring the properties of continuum tensor calculus quantities such as div and grad. And that makes it ideally suited for solving Navier-Stokes equations, which do need to satisfy equivalent continuum properties. And in particular, we investigate the use of skew symmetric operators in this research. If this work interests you, please visit us at booth number 12. Thank you.
Hello, my name is Anish Srinivas. I'm a first-year master's student of Dr. Castillo's, and in my poster, I decided to construct an algorithm for calculating higher-order mimetic operators without using the Vandermonde matrix, because using the Vandermonde matrix results into the problem of Gaussian elimination, of inverting Gaussian elimination being O of k cubed, and the condition number of the Vandermonde matrix being exploding exponentially. Instead, we use the approach of transforming it into an operator calculus problem. See poster number 13 if you're interested. Thank you.
Hi everyone, my name is Shi Luo. My topic is about efficient AI model comparison, or about finding the balance between making these models smarter and keeping their accuracy up. In this work, I use the tensor chain decomposition, which is a kind of low rank decomposition. As we all know, the lower the rank, the fewer parameters. So however, people need to select the rank for each layer manually, which is not efficient. So I designed the automatic rank determination framework. Here, after each decomposed layer, we just hook up a plug C classifier. It uses the weight imprinting technique to figure out to evaluate the layer's importance, and then we'll get the TTL score for each layer. Based on these scores, the designed rank determination algorithm will figure out the best rank for each layer, for every layer of the network. Finally, once we've got all the rank set, we are able to fine-tune the entire model to optimize the performance. That's it. Thanks.
Hello, everyone. My name is Tim Johnson. I'm a fourth-year PhD student. So the primary question that I aim to answer is how much high performance is too high performance. It's really easy just to apply your biggest, baddest algorithm to everything you have, but do you really need to? Probably not. So this is especially important in mobile devices such as edge computing, where you're in limited energy reservoirs. And so you really have to use, just enough to get by. And so this is why I investigate. You can go check it out over at poster 15. My major application is in drone navigation. This also has applications in pretty much any remote device, such as space exploration, et cetera, et cetera. Yeah, that's it. Thank you.
Reconfigurable intelligent units, reconfigurable intelligent surfaces are a new device proposed for 6G wireless communications. These devices are used to be able to reflect radio waves and higher frequency waves in any desired direction through controlling the resonance frequencies of its unit cells. One of the limitations placed on reconfigurable intelligent surfaces are its bandwidth limitations, which control the amount of information that can be reflected over this surface. My research is focused on increasing the bandwidth
of these reconfigurable intelligent units, unit cells. I've done so through implementing multiple resonating elements in the unit cell design and doing so for multiple polarizations. My name is Benjamin Bradshaw. I'm a PhD student in the computational science department. And if you'd like to know more about my research or about this technology, please come and visit me at poster number 16.
Hello everyone, my name is Shixuan Guan, a first-year PhD student at San Diego State University. My research interests include cybersecurity, cryptocurrency, and blockchain security. Today is my pleasure to present our paper titled Characterizing if the Mattress Poison Attack. This is a joint work with my advisor, Professor Kali. On Ethereum blockchain, users' accounts are addresses that consist of 40 hexadecimal characters. By exploring address shortening feature on Ethereum explorers, attacker can phishing transfer with lookalike addresses to deceive victims. So victims may mistakenly copy the wrong address and unknowingly send funds to attackers, resulting in financial loss. To detect such a new threat, we developed a detection system called Poison Hunter. By running Poison Hunter, our result shows that USDC and USDT token are primarily targeted. We detect over 14 million phishing transfers and over 6 million phishing addresses. Attackers profit nearly $90 million from over 1,800 victims. If you'd like to know more about our work, please come to our poster session at number 17. Thank you.
As some of you may know, that quantum defects in hexagon-boron nitride are promising candidates for the use of quantum information science technology towards room temperature operation. This is due to desirable spin optical properties that enable the use of qubits, quantum networks, quantum sensors, and other quantum devices. But in order to control these defects, they exist in multi-environment spaces, which add noise to your wave functions. And within these multi-environment spaces, they exponentially scale in your Hilbert space, which makes them computationally difficult to represent. My name is Antonio Corrubia. I'm a PhD student working with Dr. Sanjay Behura at San Diego State University. Please join me in poster 18, where we can talk about how we can characterize these quantum defects in hexagon-boron nitride from an exponential scaling to a polynomial order utilizing tension network states. Through the use of a quantum input-output network framework, where we can capture and retain some of the photon emission properties. Thank you.
Hi, everyone. It's truly fantastic to be here for the first time. My name is Arshia Lati. I'm working under the guidance of Dr. Humayuni and Dr. Shirazi. Accessing real-world patients' data is restricted due to privacy regulations. However, on the other hand, researchers need huge and diverse data sets to build robust machine learning models. Today, I'm here to present SceneLLM for generating synthetic data by leveraging large language models. 4 different structured prompts will be generated by our pipeline and fed to different open source large language models. And after that, the synthetic data set will be compared by the real world data set and based on different dimensions. And after that, the report will be given to the customer. And after that, hopefully in the future, we would like just to incorporate federated learning environment to increase the privacy. Thank you so much.
All right. Hello, everyone. My name is Najee George. I am a PhD student working with Professor Jorge at UCI, particularly analyzing molecular dynamic situations, simulations, I should say. Particularly, we're looking at notable errors, propagation errors that can occur during these simulations, and trying to ask ourselves, can we overcome these errors? One particularly is stability errors that can occur due to the size of a time step, So to do this, I'm looking at Tully's fewest switches surface hopping. And I'm paying particular attention to the surface hopping step, and I'm implementing various finite differencing algorithms during that step. I'm implementing a first order algorithm, a second order algorithm, and a fourth order algorithm, and trying to see how this one simple change can affect the behavior of our simulated chemical reaction. My poster presentation is mainly focused on the energy conservation, but I'm also looking at excited state decomposition and product distribution. If you want to know more, please come to my poster at poster 20. Thank you.